Hello, grade 8. This is Mrs. Lopez. We are in module 1, lesson 8, estimating quantities. So, in the previous lesson, we learned the powers of 10, and we learned that we can always look at the magnitude of a number and to see how big or small it is. Uh, this In this one, we are estimating quantities. We are trying to see where that number goes on the number line, pretty much. So let's look at example 1. In 1723, the population of New York City was approximately 7,248. By 1870, almost 150 years later, the population had grown to 942,292. We want to determine approximately how many times greater the population was in 1870 compared to 1723. So the word approximately in question 1, in the question, lets us know that we do not need to find a precise answer. So we just approximate to the powers of 10. That's all we do. So the population in 1723 was 7,248. We know that 7,248 is about 10,000, which is 10 to the fourth. We are rounding to the power of 10. We learned in lesson 7 that 7,248 has 4 digits, and so 10 to the fourth power will be the one exceeding it, right? Population in 1870 is 942,292. It has 6 digits, so 10 to the sixth will be a good approximation for that number as well. So it's about 1 million, right? Now we want to compare the population in 1870 to the population 1723. So, if we look in the problem, it says how many times greater. That word times, how many times greater, shows that we need to divide to find how many times one is greater than the other. And we are comparing this 1870 to 1723. So the population in 1870 will come first in the numerator, and in the denominator we are going to have the population in 1723. We are dividing two numbers. Now notice we have the same base and different exponents. We know that by the rule of dividing like bases with exponents, we need to subtract the exponents. So when we have 10 to the 6th over 10 to the 4th, we get 10 to the power of 6 minus 4, which is 10 to the 2nd. Therefore, there were approximately 100 times more people in New York City in 1870 compared to 1723, because we know that 10 to the 2nd is 100, right? So there are approximately 100 times more people. It is easier to do when we don't have to use a calculator, or since we can subtract better than we can divide, it's a lot easier to do. Let's look at exercise 1 and see if we can do it by ourselves with this example in mind. The Federal Reserve states that the average household in January of 2013 had $7,122 in credit card debt. So that is household debt, credit card debt. About how many times greater is the U.S. national debt? U.S. national debt is 16,755,133,009,522. This is very hard to pronounce, and so it's very hard to be able to figure out how many times greater this number than this one. So we are going to approximate, and since we are looking at about how many, we are going to approximate using our powers of 10. So the U.S. national debt is that big of a number. That big of a number has 3, 6, 9, 12, 13, 14 digits. Since it has 14 digits, it's about what? It's about 10 to the 14th power. It's about 10 to the 14th power. Let's look at the household debt. Because this number has 4 digits, so it's about 10 to the 4th. To find out how many times greater, we are going to divide the US debt, 10 to the 14th, by 10 to the 4th. Since again we are dividing like bases with exponents, we are going to subtract exponents, and we will get 10 to the 10th. I'm not going to write how much exactly that number is because it's going to be too big of a number. But I know that the US national debt is about 10 to the 10th times greater than the average household debt. Okay, let's write the answer down. The US national debt is about 10 to the 10th times greater than the average household's credit card debt. Okay, so we know how to compare the quantities right now, right? To find out how many times one quantity is bigger than the other, we are going to divide. Let's look at exercise 2. There are about 3 million students attending school, kindergarten through grade 12 in New York. Express the number of students as a single-digit integer times the power of 10. So let's look at this 3 million. 3 million is 3 multiplied by 1 million, right? 3 multiplied by 1 million. And that 1 million I can write as 10 to the 6th power because that has 6 digits. So 3 times 10 to the 6th. The average number of students attending middle school in New York is 8 times 10 to the 2nd. How many times greater is the overall number of K to 12 students compared to the average number of middle school students? So we are looking at which one we are looking at. So this is a middle school right here. That's the middle school. And this one is the whole K through 12, right? So we are comparing this number to this number to see how many times this one is greater than this one. So we are going to divide 3 times 10 to the 6th by 8 times 10 to the 2nd. This is a problem that we saw before when we learned about the rules of exponents. Here I have 3 eighths, and here I have the like bases with the powers that I'm subtracting, right? So I'll get 3 eighths times 10 to the 4th. Since I'm subtracting, I'm getting the 4th power. Now, this one is pretty hard to say what that real number really is, right? So I am actually going to change it into a decimal. 3 eighths, and I can use a calculator to divide 3 by 8, is 375 thousandths times 10 to the 4th. And since 10 to the 4th is 10,000, I'm actually going to multiply by 10,000. And so when I'm multiplying a number by 10,000, all I'm doing is moving my decimal point to the right since the big number becomes bigger 4 times. 1, 2, 3, 4. And I get 3,750 times. So the overall number of K through 12 students, the overall number of K through 12 students is about, since we were rounding up, is about 3,750 times greater than the average number of middle school students. Than the average number of middle school students. Okay. Exercise 3. A conservative estimate of the number of stars in the universe is 6 times 10 to the 22nd. The average human can see about 3,000 stars at night with his naked eye. About how many times more stars are there in the universe compared to the stars a human can actually see? So that's the number of stars in the universe. That's the number of stars that the human can see. We are going to compare these two and to see about how many times more stars are there in the universe. So we're looking at times, right? We are going to divide one by the other. Since we are comparing the universe to the human, first we want to change 3,000 into a number multiplied by the power of 10. So we have 3,000 is 3 times 1,000, right? And that is 3 times 10 to the third. So now that we are ready, we can write down 6 times 10 to the 22nd over 3 times 10 to the third. And now I will be able to use my powers of exponents, rules of exponents, to simplify this equation. So 6 over 3 is 2. And I'm multiplying that by 10 to the power of 22 minus 3, and that is 2 to the 10, and 2 times 10 to the 19th power. Okay, exercise 4. And I think that's the last one before homework starts. Oh, no, not yet. Exercise 4. The estimated world population in 2011 was 7 times 10 to the 9th. Of the total population, 682 million of those people were left-handed. Approximately what percentage of the world population is left-handed according to the 2011 estimation? So we are looking at the world population to left-handed people. So we have the world population is 7 times 10 to the 9th, and 682 million is 682 times million, right? And so what I want to do is, let me actually see how they're approximating it. So to see how much about that is. So 682 million is going to be about 700 million, right? And that is 7 times 10 to the 8th power, because I have 8 zeros in here. So 7 times 10 to the 8th. So I'm going to divide 7 times 10 to the 9th, which is our world population, by 7 times 10 to the 8th, which is our left-handed people. And we will get, we are going to simplify 7 and 7, that's 1. And we have 10 to the ninth minus 10 to the eighth, and we will get 10. Okay, so 10 is, let's see, this is our world population, and this is our left-handed. I actually made a mistake here because I want to see a percent of left-handed to the world population, right? So I will have to actually do it the other way around. I'm sorry about that. So I have 7 times 10 to the 8th over 7 times 10 to the ninth, and I will get 10 to the negative first, which is 1/10. And 1/10 is about 10%, which is not about, it actually is 10%. 1/10 is 10%. So that's what it is right here. I'm sorry about this. This is not right. Okay. About 1/10 of your population is left-handed, which is 10% according to 2011 estimation. All right. Example 4. The average American household spends about $40,000 each year. And this is an example, so we are going to go through the whole thing. If there are about 1 times 10 to the 8th households, what is the total amount of money spent by American households in 1 year? So this is an average household. The average household, we are going to write using the number multiplied by the powers of 10. So we have 4 times 10 to the 4th. Now, we have that many households. This is just one household. How do I find out how much money spent by everyone, by all households in 1 year? This is 1. This is how many households. So I'm going to multiply this 1 by this many households. So the question asks us how much money all American households spend in 1 year, which means that we need to multiply the amount spent by one household by the total number of households. So I have 4 times 10 to the 4th, which is this one, multiplied by 1 times 10 to the 8th, which is this one. By the rule of commutative property of multiplication, I can switch numbers around. What is this exactly? This is 4 times 10 to the 4th times 1 times 10 to the 8th. So what we are really doing, we are just changing 10 to the 4th and 1 to put these two together. And I will be able to multiply 4 times 1, and I will be able to add the exponents over here. So I will have 4 times 1 is 4, and 10 to the 4th times 10 to the 8th, I'm adding the exponents, is 10 to the 12th. 4 times 10 to the 12th. Therefore, American households spend about 4 trillion each year altogether. That is a big number. That is a lot of money too. So, exercise 5. The average person takes about 30,000 breaths per day. Okay. Express this number as a single-digit integer times the power of 10. 30,000 is 3 times 10 to the 4th, because we want one single-digit integer. 30,000 is 30 times 1,000, which is 3 times 10,000, right? So 3 times 10 to the 4th. If the average American lives about 80 years, which is about 30,000 days, how many total breaths will a person take in her lifetime? So here we have breaths per day. Here we have how many days we have. So we are going to multiply this number by this number. This number we need to also express as a single-digit integer multiplied by the power of 10. So that is also going to be 3 times 10 to the 4th. Okay, so now we are going to multiply the two numbers together. 3 times 10 to the 4th, and I'm going to multiply that by 3 times 10 to the 4th. Since it's only multiplication, I can change the numbers around according to the commutative property of multiplication. So I can do 3 times 3 times 10 to the fourth times 10 to the fourth. 3 times 3 is 9. 10 to the fourth times 10 to the fourth is 10 to the eighth. And I'm not going to convert that into a whole number. So we will have 9 times 10 to the eighth breaths a person can take in a lifetime. Okay? All right. So now this is a problem set. Problem set can be a little bit tricky. I definitely want you to do number 1. And I definitely want you to do number 3 and 4. And number 2, I'm sure you can figure it out. I want you to try it. So I'm going to put a star next to it because we have not done the calculator problem. You can work on it at home. And if you can understand this, let me know. Okay? I will see you in class.